Hey students. All right, so next section is on measures of location. So up to this point, we've talked about visual summaries, and visual summaries are nice. The thing is, though, we don't want to restrict ourselves just to visual summaries. We would also like to be able to have numerical measures of data to understand distributions. So we're going to start with measures of location. Measures of location tell us where a dataset tends to be located along a number line. So the first and most common measure, you probably have already seen a lot of these measures that we're going to talk about, but the very first one we're going to talk about is the sample mean. And for a dataset consisting of observations x1 to xn, the sample mean is defined as x bar, which equals 1 divided by n times the sum from I equals 1 to n xi. Which, if you're not familiar with this notation, what this means is we would take our data set, add up everything in the data set, and then divide the resulting sum by n. Now, there's this thing called the sample proportion. And in fact, relative frequencies are sample proportions. They're counting the proportion of observations in a sample that take a certain value. The sample proportion is also a measure of location. It loosely is like the proportion of observations in the sample that have a certain characteristic. So we divide the sample into successes and failures. We like to use that vocabulary of success and failure. A success, and the sample proportion will count the number of successes. So we'll have p hat equals, and very loosely, we're just going to say this is the number of whatever we consider to be a success, and divide this by the sample size. Now, this could also be written as x over n, which could also, where x is this number of successes. And then we could say, let's suppose that xi is equal to 1 if the ith observation counts as a success and 0 otherwise. What then does it mean to count the number of successes? To count the number of successes is to go through each observation and then add 1 to a running count if that observation counts as a success, and otherwise do nothing, which is the same as adding 0. So we could then say that the number of successes is equal to the sum from I equals 1 to n of this new xi variable that is counting the number of successes effectively and saying whether an observation is a success. So we should say that this sum is equal to the number of successes. And then we take this sum and divide it by n, which is also, for what it's worth, the same as taking the sum and multiplying it by 1 over n. So notice what I just wrote down. I just wrote down the sample mean again, which means that the sample proportion is the same as the sample mean of a sample that consists of 1s for successes and 0s otherwise. So recognizing this is actually very important, because in probability theory, the mean, or more directly, sums of variables or sums of random variables, are very important. So recognizing something as a sample mean means that any theorems from probability theory that involve the sample mean can be applied to that variable. So this is actually quite important to recognize. But that means that after this point, we really don't have to say much more about sample proportions, because the sample mean, whenever we're talking about the sample mean, we're also talking about sample proportions. So let's get started with an example. What is the average number of points your daughter's soccer team scores. Here is, as a reminder, the data set. This is actually proper R code right here, just to write down the variable name soccer. And what will happen is R will then print out that data set. So, but we're just going to take that for granted for now and compute first. Let's go ahead and compute the sum of these numbers. So the sum from I equals 1 to n xi, which is basically this right here, just means take all the numbers in this data set and add them up. So we've got 9 plus 6 is 15, plus 5 is 20, plus 5 is 25, plus 5 is 30, plus 6 is 36, plus 2 is 38, plus 8 is 46, plus 3 is 49, plus 4 is 53, plus 8 is 51, plus... Oh, it looks like I'm... Alright, so I actually have something written down. I have 62. I think I might have missed something in that count, but it's going to add up to 62. Okay, so just take my word for it. So this adds up to 62. N is equal to 12. So the sample size is equal to 12. And the sample mean then, x bar, will be 62 divided by 12, which equals 31 over 6, which is equal to 5.16 with a repeating 6. Okay? If we were to go to the next page in these notes, we would see some R code that computes the sample mean for this data set. The R function is mean. So we say mean of the soccer data set, and it will report to us the mean, which is what we computed. Now let's suppose that R1 to Rn is the ordered version of this data set. So x1 to xn is just... So R1 to Rn is x1 to xn, but ordered. Remember from a previous video for section 2 on that for this notation, x1 to xn, I do not necessarily imply any sort of ordering. Now I do. For R1 to Rn, I'm going to imply an ordering. The sample median is another measure for the location of the data set. It is defined as the number that splits this data set in half. So that is basically the definition. And from that, we can come up with mathematical formula. So we can say that x tilde, that's the notation we will use for the sample median. X tilde will be one of two possibilities. First, there is the case when there are an odd number of observations. If there are an odd number of observations, let's see, let's zoom in so I can have a little bit more precise writing. If there are an odd number of observations, after we order the data set, the observation in the position n plus 1 divided by 2 will be the number that splits the data set in half. So this will be what we're using if n is odd. So to think about this, if we had 11 observations, 11 plus 1 divided by 2, so that's 12 divided by 2, that's equal to 6. The sixth observation, after you order the data set, will be the median. Okay? Now suppose that there are an even number of observations. We could potentially choose the observation in the n over 2th position. So if the sample size were 12, this would be the sixth ordered observation. Or we could potentially have the 7th ordered observation. Both of those are kind of dividing the center. So what we'll do instead is we will take the midpoint between these two numbers, which could potentially end up being the same number. There's nothing that says that these two numbers are not the same. But we're just going to average those two numbers, take the midpoint in between them. And admittedly, if you had a number line and you had some data over here and some data over here, and you have these two observations as being potentially the median. Any number in between them could be defined as the median, since any of those numbers would divide the data set in half. And in fact, you may see alternative definitions of the median in R to take advantage of this fact. But for now, it doesn't really matter if we had a lot of observations how exactly we define the median. This is perfectly fine to just take the midpoint between the ordered observation in the position n over 2 and the ordered observation in the position n over 2 plus 1. So if we had 12 observations, we would take the 6th and the 7th observations and average them to get the median. Okay. Let's see an example of computing the median. Find the median of the first 11 soccer games your daughter's team participated in. I chose 11 just to have an even number to kind of... odd number, just for demonstration purposes. In this case, the sort function in R, this function will order your data set from smallest to largest. Given a vector, it will order that vector from smallest to largest. So we have sorted this data set. We now have an ordered data set. And I want to compute the median of that data set. Well, first off, there are n equals 11 observations in this data set. That means that the observation in the middle will be n plus 1 over 2, which is 12 over 2, which equals 6. Therefore, the median will be the 6th ordered observation, which is, well, let's see, 1, 2, 3, 4, 5, 6. 5. So it will be 5. That will be the median. If we were to look at some R code, there is a function, an R function called median, and given that data set, by the way, I didn't mention this before, this right here, this square bracket stuff, this is subsetting notation. It basically translates to get the observations, get all observations between the 1st and the 11th in this data set. Okay? And remember that soccer itself is not ordered, so we're just getting observations x1 through x11. Okay? But I just feed that vector to the median function, and it tells me that the median is 5. And by the way, if you're wondering what this little 1 right here means, that's just part of how R prints vectors. If this vector was quite long, it would split over a number of lines, and this little 1 would just be tracking which observation you're looking at with each line. So you wouldn't have, so like if there was 10 down, so if there was like more numbers after this, and then we had in square brackets 10 and saw the number 6 and numbers after that, this would tell us that the 6th number in that that would tell us that the 10th number in that vector was 6. It's just something that's supposed to make reading what's in vectors visually easier. Okay, so I think I pressed something. Let's do that. Okay. All right. So continuing on, other measures of location are percentiles. So we're going to say that this is the Greek letter alpha, and alpha is a number between 0 and 1, and we're going to include 0 and 1 as well. The alpha times 100th percentile is the number such that roughly alpha times 100% of the data in the ordered data set lies to the left of that number. So if we choose alpha equals 0.5, that would be the 50th percentile. So roughly 50% of the data set lies to the left of that number, which means that 50% lies to the right. And what I just described is the median, because the median is the observation that splits the data set in half, which means that half of the data set is to the left, or 50%, and 50% is to the right. So the median actually counts as a percentile. Percentiles are a generalization of the notion of a median. In fact, there are other percentiles that we care about, such as quartiles. Quartiles divide the data set up into quarters. So for the first quartile, roughly 25% of the data set rise to the left of that quartile. And for the third quartile, roughly 75% of the data set lies to the left of that quartile. So to visualize, we would have the first, second, and third quartiles, and roughly 25% lies to the left of the first quartile, and roughly 75% of the data set lies to the left of the third quartile. And the second quartile is the quartile where roughly 50% lies to the left of that quartile. In other words, the median again. You can also say that there is a 0th quartile, which corresponds to alpha equals 0. Alpha equals 0 means that there is nothing really to the left of this observation. So that would correspond to the sample minimum. Whereas alpha equals 1 means that about 100% of the data set lies to the left of that number. That corresponds to the sample maximum. There are actually a number of procedures for computing percentiles from data sets, and I'm not going to repeat all of those procedures. If anything, I'm just going to list off the procedure that's easiest to do by hand, because at the end of the day, in the real world, what you would do is ask R to get a percentile, and R has its own algorithm for getting percentiles that's more complicated than what we're about to do. And I really don't see the point in telling introductory students how to do that, because it's more computationally intensive, and like, what's the point? If you're doing things by hand, let's keep things simple. I should also probably mention, if you combine the 0th, first, second, third, and fourth quartile is the maximum. If you combine those together, you end up with what's known as the 5-number summary of a data set. So, here's a procedure for finding quartiles. First, find the median of the data set. Then split the data set into 2 data sets at the median. And we're working with the ordered data set now. So split it into 2 data sets at the median. If n is odd, remove the data point that corresponds to the median. And then, to find the first quartile, find the median of the lower data set. And then, to find the third quartile, find the median of the upper data set. So to visualize this procedure, we have a data set, find the median, and this will split the data set into 2, then find the medians of the other 2 halves. Okay? That will tell you what the first and third quartile are. The minimum and the maximum are easy. Find the smallest and the largest numbers in the ordered data set. Okay, so for our first example, we're going to find the first and third quartiles of this little girl's first 11 soccer games. So let me get caught up in my notes for a second. Okay, so to find these 2 quartiles, how about we write down what that data set was, just for our own purposes. So we've got 2, 3, 4, 5, 5, 5, 6, 6, 8, 9. Okay, so the median was 5, and this is an odd number data set, so we're going to delete that median. 6, 6. Oh, oops, there were 2 8s. Sorry about that. So we're going to delete the median, which is 5, and then we have split the data set in 2. So then we find the median of the first half. There is an odd number of observations here. So the median will be 4. Thus, the first quartile, which I will call Q1, that will be 4. And the median of the upper data set, that will be 8. So that means that the third quartile will be 8. And if we wanted to, we can kind of fill out the 5-number summary, saying the second quartile, which is the median, that number is going to be 5. The 0th quartile, which is the minimum, well, that's going to be 2. 2 is the smallest number. And the 4th quartile, which is the maximum, Well, the largest number in the data set is 9, so that will be 9. Okay? Okay, next example. Find the 10th and 90th percentiles of the height data. I have listed the data for you below in order. So the data set, oh yeah, this is actually what I was getting to regarding those little numbers in square brackets. This is the 9th observation, right? So that means that this number right here is the 10th observation in the data set. So that means that this data set has n equals 10 observations. So 10th percentile, so roughly 10% of the data set lies to the left of that number. So 0.1 times 10 is equal to 1. So that's about one number lies there. So we're going to choose 5.05. So 5.05 will be the 10th percentile, which we will call that Q hat point 10. And for the 90th percentile, so 0.9 times 10, that's going to be 9. So that's observation number 9. So 90% of the data set lies, including that number, to the left of 5.63. So we'll say that 5.63 will be the 90th percentile, which we'll call Q hat 90. Okay? And actually, R has functions for computing quantiles. Another word for what we're talking about here are quantiles. Here I have asked R specifically to give me the 25th and 75th percentiles. It is not using this procedure that I described. It is using a different procedure for finding quantiles. There's a number of different procedures for finding quantiles and percentiles. And if your sample size is large, nobody cares which one you use, really. It really only matters at smaller sample sizes which procedure exactly you use, and there are various different motivations for different kinds of procedures. There's various ways to solve the same problem, and what I described is simple enough to do by hand. So if you're going to do it by hand, go ahead and use what I used. This is probably whatever came up with this is probably much more complicated. And if you need something more complicated, then don't do it by hand. Ask R to do it. So you can read R's documentation to see what exactly is being done here. It's using some sort of interpolation trick. So here I've asked, so the second parameter here, this is a vector that contains the numbers 0.25 and 0.75 corresponding to the 25th and 75th percentiles, or quantiles. I'm not really sure what the difference between those two words is. Here I asked for the 10th and 90th quantiles or percentiles, and it gives me numbers. These are all pretty close to what I came up with before. Okay, next up, let's kind of, we've come up with some measures of location, and there's actually a number of different measures of location. Like, for example, I have seen a measure where you take the largest and the smallest observations. So you could say that's Rn minus R1, plus R1. So take the midpoint between the largest and the smallest observations. That's actually another measure of location. There's a number of different measures of location. What I've shown here so far is fine, but let's go ahead and start comparing these different methods for describing the location of a data set. So the sample mean x bar is known to be sensitive to outliers, which means that outliers in the data set have a profound effect on the sample mean. So if you had, for example, a data set that consists of let's say 1, 2, 3, the average of that data set, or the mean of that data set, will be 2. And the median of that data set will also be 2. Compare that to a data set that contains the numbers 1 to 1,000. So the mean of that is going to be about 500, which is much larger than 2, what it was before. Compare that to the median. The median of that data set, 1 to 1,000, is still 2, which means that the median is insensitive to outliers. It basically doesn't care what they are. All it cares about is the ordering of the observations, so long as an outlier, if you were to change the value of an outlier, so long as it doesn't change the ordering of the data set, the median will not change. So as an example of this, I'm going to compute the sample mean and the sample mean of the daughter's soccer games if I throw in a 12th soccer game. And I'm going to consider a number of different scenarios where her 12th game was 1 point or 1 goal, 4 goals, 2 goals, and 18 goals. We're going to consider that. And what I actually did here was I created a vector that contains these. So I'm not going to talk too much more about this because I want to focus on the math. First off, when I add up the 11 other games, when I add those up, I end up with a cumulative score of 61. So let's create a table for all of these potential outliers. So in this table, we're going to consider when the 12th game is 1, when it's 4, when it's 2, and when it's 18. And we're going to have a column for the sum of the observations. We're going to have a column for the sample mean and a column for the sample median. So in the case where the 12th game is 1, this will add up to 62. And by the way, I'm using the word outlier for 1, but 1 in this case would not be an outlier. Same with 4 and 2, but 18 certainly would be considered an outlier. So if her 12th game is 1, then it adds up to 62. If her 12th game is 4, it adds up to 65. If her 12th game is 2, the game's cumulative score is going to be not 62, 63. And if it's 18, they all add up to 79. And then we're going to take these sums and divide them by 12. In the end, we end up with, in the first case, we get a sample mean of 5.16. In the second case, we get a sample mean of 5.416. Repeating 6. In the third case, we get 5.25. And in the fourth case, we get 6.58, which is much different from what we had before. Hold on. I think my pen might be... Okay, my pen's back. Is it, though? Might need to charge. Okay, now the median. In the first case... So in the first case... the median is still going to be 5. And in fact, it's going to be 5 for the first 3 cases because the median was 5 and it didn't change the order of the data set. If you go back and look at the original data set, we're essentially in these first 3 cases, we shift all the numbers to the left, which means that the median is going to be the number to the left of what it was before, which was 5. But if we chose, or it's actually going to be the average of 5 and 5, which is still 5. But in the last case, the median actually will be the average of 5 and 6. So it will be 5.5. So the median did change a little bit in the last case, but it's mostly because of where that outlier ended up. It ended up on the right-hand side of the data set, or the right-hand side of what the median was before. And it could have been 273, and the median would be exactly the same. But as we can see, the median isn't changing really at all, especially when you compare it to the mean. And here is some R code that the idea of this code is I'm going through a loop, adding this observation to a version of the data set, and then computing the median and the mean of that data set. The result will be an R matrix. I take the transpose of that matrix because that's the version of the matrix that I prefer. I'm giving the matrix some row names and column names, do some rounding, and this is the resulting matrix. and it's pretty similar to what we had before. In fact, there is a relationship that we can say in general between the mean and the median, depending on whether the data is negatively skewed, positively skewed, or symmetric. If the data set is positively skewed, so the data set looks roughly like this, then the median, which is the point that divides the data set roughly in half, will be less than the mean. And that's because the mean is going to try to chase the outliers, and the outliers are going to be on the right-hand side of the bulk of the data. So, in the case of negatively skewed data, we're going to have the opposite relationship, where the median, since the outliers are going to be on the left-hand side of the bulk of the data, the mean is going to chase the smaller numbers. So the median will tend to be greater than the mean. And in the case of a symmetric data set, the mean and the median should be approximately the same. In real data, probabilistically, when we talk about means and medians and probability, they will be exactly the same when the distribution of the data is symmetric. But in real data, that's never the case. In real data, they will just be close, and what it means to be close is like that's a judgment call, right? So what would some implications for that? Thinking back to some examples of positively skewed and negatively skewed data sets, I said that a positively skewed data set is incomes. This relationship means that the average income tends to be larger than the median income. And economists generally prefer to use the median income for income distributions because it seems inappropriate to use the mean. This kind of gets to the issue of, I've given you these competing measures for means and for measuring the location of a data set. Which one of these measures should you use? I would say use the one that's appropriate, which means, here's one thing. When should you use the mean? I would say you should use the mean when large observations are allowed to compensate for small ones. Let's say, for example, that you're gambling. If you're gambling, what you care about are your mean earnings and not your median earnings. Because it's okay for you to win nothing 99 times if you win a million, or I guess it also depends on how much this game is worth. But let's say that you're playing a game that costs $1 each time you play. It's okay for you to win nothing 99 times if on the 100th time you win $1 million. That would be awesome for you. Whereas in that situation, the median would be $0. And if you were judging by the median how well you were doing, you would think you were actually doing poorly. So if you're allowing large observations or small observations to maybe replace or detract from the overall score, then the mean is appropriate. On the other hand, the median in the case of social sciences, we care more about what 50% of the population is experiencing, and we don't necessarily want to allow the great fortune of the wealthy to compensate for the great poverty of the very poor. So in that situation, the median would be the preferred observation. And of course, if theoretically what you're trying to measure is the population median, then you should use the sample median. And if you're trying to estimate the population mean, you should use the sample mean. And in which case you should not be using the opposite. Now, there are some exceptions to this, and we'll talk about this when we talk about probability and talk about hypothesis testing. There's notions such as most powerful tests, like if your data set was symmetric and you knew it came from a normal distribution, you should always use the mean, even if what you care about is the median. And the reason why that is because for a normal distribution, the two numbers are the same. But we're just going to leave that for now. So all of this was talking about sample results. There are analogous population numbers too. Okay, so I just want to very quickly satisfy my nervousness. Okay, we're still streaming. Okay. All right, there is another measure for location called the trimmed mean. So I'm going to tell you about the trimmed mean, and I'm even going to compute it for you. But then I'm going to have some caveats about using it. You probably should not be using the trimmed mean, and I'll explain that in a second. But the idea of the trimmed mean is we have the median, and the median is not sensitive to outliers, which is generally considered a blessing, but it's not always a good thing because it feels a little inappropriate to throw out so much data when you're computing the median, because once you know the ordering of the data and you know which one or two numbers are in the middle, then the rest of the data doesn't matter, and that feels a little extreme. On the other hand, you're a little bothered by the mean's sensitivity to outliers. Furthermore, on outliers, you might think, should we throw out outliers? Should we ignore outliers? Because that's actually kind of what the trimmed mean is suggesting that we should do. With the trimmed mean, what we're going to do is we're going to use only... we're going to throw out a certain percentage of the data. Like, we're going to throw out 10% on the left-hand side and 10% on the right-hand side of the data set. So throw out the 10% of the smallest numbers and 10% so in this data set, 10% of the numbers that are the smallest numbers of the data set and 10% of the numbers that are the larger numbers in the data set. That would be the trim mean where alpha equals 0.1, where you're trimming at 10% on each end. So the idea of the trim mean is throw out the outliers. So on this issue of whether you should throw out outliers, you should actually think very carefully before you throw out outliers in general. If you're computing a trimmed mean, then that's kind of what you're doing. But let's say you look at a data set and you see that your estimators are actually very influenced by a couple outliers, and you're thinking, maybe I should just throw those out. I would first ask, why are you throwing them out? Are you throwing it out because you think the number is erroneous? Because I, in my own experience, have seen numbers in data sets where it's like, that's probably an error. Someone probably entered the wrong number, so I'm going to throw it out. Like when someone writes in the American Community Survey that someone's made $1 trillion, it's like, that's probably not correct. You should just throw it out. If that's what's going on, go ahead and throw it out, because the reason why you're throwing it out is because of data contamination. But if you're throwing it out just because it's causing bad behavior in your estimators, that is probably inappropriate. And you should instead try to model the outlier or just accept it rather than throw it out. Or think harder about why it is that you are using the mean rather than the median. I would actually suggest that over throwing the outlier out. But anyway, let's go ahead and compute the trimmed mean for the height data set. So let's go ahead and rewrite that data set. We've got, I don't want blue. Okay, so I've got, for the height data set, 5.05. You can go ahead and skip ahead a little bit to skip me writing down numbers. So 5.05, 5.13, 5.21, 5.3, 5.3. This splits the data set in half. So the next number is 5.38. And we've got 5.38 again. 5.55. 5.63 and 5.96. Okay, so there are 10 numbers in this data set. If we're going to trim, so if we're going to say alpha equals 0.1, so we're going to trim 10% of the data off on each end. So trim 10% at each end. that means that we're going to end up trimming zero point 0.1 times 10, where 10 is the sample size, which is 1. We're going to trim off the smallest and the largest number in this data set. So that would be 5.05 and 5.96. And then take the average of the remaining data set. So, in that case, X bar, where we trim off 10%, will be the average of the 8 remaining numbers, where we're sum from I equals 2 to 9, the ordered data set. And that is going to end up being 42. So the sum is going to be 42.88. And then we divide that by 8, and the result will be 5.36. So 5.36 feet, because this data set is in feet. We're talking about height. Okay, and R can compute trimmed means. In fact, you can just use the mean function like we had before. We're just going to pass it an additional parameter that tells the function to trim. Now, I mentioned a little while back, you actually probably should not be computing trimmed means. And the reason why is because when we compute a median, which a little side note, I guess the median, both the mean and the median count as particular trimmed means, where the median is like the trimmed mean where you trim off 50%, and the mean is the trimmed mean where you trim off 0%. So the trimmed mean kind of generalizes these other two statistics, but you probably should only use those other two statistics. You should probably not use the trimmed mean. I mean, I guess if what you were doing is instead of taking off 10% on either end, it's like always take off the 2 largest and 2 smallest numbers. That could be appropriate from a theoretical perspective. So because basically, as you increase the sample size, the number of observations that you're trimming off becomes very small relative to the rest of the sample. But trimming off 10% at either end from a theoretical standing is a little odd. And the reason why is that there is actually a population median that we are estimating when we are using a sample median. And there is a population mean that we are estimating when we use a sample mean, and both of those quantities are very well understood. But when you're using a trimmed mean, you are estimating neither of those things. You're estimating some weird hybrid, monstrous population statistic that we don't necessarily understand. You're estimating essentially the population version of a trimmed mean, and it's questionable whether that's actually what you want. It seems like the worst of both worlds in that case, because no one can actually, like, why would we talk about the population except for the 10% largest and 10% smallest numbers? Like, that doesn't really make a whole lot of sense. So, for that reason, unless you are actually, I would actually more advocate for like a fixed trimming where you take off the 2 largest and 2 smallest observations. Although at that point, you probably should just use the mean or use the median. I probably would not use the trimmed mean. So, okay, so that's it for this section. In the next section, we will be discussing measures of variability. So I will cut it off here and have a good day.